Let's start chapter 11. First section today we're going to talk about is sequences. I'm going to introduce what is a sequence. There are some properties for each sequence, like is it an increasing, decreasing sequence, bounds for sequences. So first, what is sequence? Sequence is a set of numbers with a definitive order. So let's say you have first element, second element, third element, and so on of the set. So these AIs, A1 the first element, A2 is the second element, A third, and so on. Anth is the nth element of the set. And this is like, you can represent the sequence by writing out all the terms of that sequence. This is one way to show it. Another way to show it is to define the sequence in terms with a formula. So you say an is a function of n. You give an input, that would be the nth term of that sequence. And there's a preceding notation that tells you basically n starts from where to infinity goes on, and an is exactly the same representation that you get in the defining formula. All these notations are equivalent, so one should represent the other and so on. So not always you have all three, you can get one from the other. It's quite simple. So here is an example. Let's look at this example. N divided by n plus 1 is the sequence given where the first term starts with n equal to 1 up to the infinity. Is you can increase n integer wise. So n, if you let n to be 1, what do we get is you get 1 divided by 1 plus 1, which would be 1 divided by 2. So the first term of the sequence would be 1/2. If you let n equal to 2, so this is a first, a second would be replace n with 2. That would be second entry, 2 divided by 2 plus 1, or 2/3. And third entry would be replace 3. And so this is the nth entry, nth term of the sequence. Okay, so not that difficult if you're given this preceding formula. So what is the corresponding formula? The defining formula is the an is basically represented by n divided by n plus 1. And our initial assumption is that n is greater than or equal to 1. Not always you start with 1, but in this case we can start with 1 and you get this corresponding sequence. We could have started with 0 as well. Normally we assume that we start with 1, but always that's not the case. So here what we should notice that you're given all the three forms of this sequence. So what if you only given the preceding notation? Can you come up with a defining formula, as well as can you write out some of the terms of this formula? So here's an example. For example, cosine n pi over 6. Maybe use a parentheses here. And they ask you find out the defining formula of this sequence. So what would be the defining formula? Simply it would be cosine n pi over 6, and our assumption is that n must start with 1. So this is quite easy. How about if we want to find out the terms of this formula? What would be a1? A1 would be replace n with 1, so you get cosine pi over 6. And a2 would be replace n with 2, so cosine 2 pi over 6, and so on. The a3 would be cosine 3 pi over 6, dot dot dot, and the nth term would be exactly the same. But you can simplify this and say, okay, cosine pi over 6, we know that it is root 3 over 2. Cosine 2 pi over 6 would be 1/2. Cosine 3 pi over 6 or pi half would be 0, and you can come up with the sequence this way as well. They are the same thing. Okay, so the representation of the sequence by writing it term by term, maybe this is easier to see the formula than that one. But the question would be, is it possible to come back and given from the sequence term, write out the defining formula of the sequence? Not always that easy. So here, if they give you the formula, can you write the preceding notation? So the preceding notation, we notice that I wrote it today. The assumption here is n greater than or equal to 3, because if you replace negative number, you'll get imaginary values. So our assumption is that you replace n and you have a positive value or 0 underneath the square root. So the defining formula is square root of n minus 3. N starts from 3. Okay, so the first entry, a1, is not an option because you'll get a1 means starting from the first entry. Sometimes there is a shift in the notation. So instead of writing it this way, so here a1, we don't have a1. a2, we don't have it based on our notation a. So a3, now I can find out what is a3. a3 would be replaced 3 and 0. And then after that, you'll get square root of 1, square root of 2, and that. Okay, so sometimes to avoid writing these first two terms, and say we don't have those terms because you should start with n. So this would be, in that case, this would be the first term. First term of the sequence, because these two terms are not really defined. So they introduce a new variable, maybe like b, and write this is the b1. This would be the b2, b3. There is a relation between a and b, is just a shift. So instead of writing an, they write bn, the square root of n greater than or equal to, n plus 1, n minus 1, n greater than or equal to 1. Now if you compare these two, replace n with 1, what you get is, you get b1, b1 would be 0. Replace n with 2, you get b2, b2 would be square root of 1. So on. So what you've done is basically you shift the n2 to the left. So instead of n, you wrote n plus 2. By doing this, this n kind of added 2, subtract 2 from both sides. You basically get n start from 1. Okay, you can assume that I combined n minus 3, right, as n minus 2 minus 1. That's how you can think about it. And I call this a new n. Okay, let's not go too far with this shift for the moment. We'll come back to this, but just I wanted to mention that it's important that the initial value, where do you start with? Okay, so here, what if they give you a sequence of terms and they don't give you the formula? Can you come up with a formula? Normally, one thing that you always need to notice is if you have an alternating terms like this, plus, minus, ignore the 1, just the sign. That means there is negative 1 to some power n. If n is 1, then you'll get negative 1. If n is 2, then you'll get 1. If n is 3, you'll get again negative. So this kind of alternating sign always comes from this negative 1 to the power n. So I can say an involves negative 1 to power n, multiply by, the numerator in this case is simply 1, so multiply by 1, divide by, what is the denominator? The denominator is 2 to the power 1, 2 to the power 2, 2 to the power 3, so basically 2 to the power n. And we start with n is starting with 1. The first entry would be negative 1/2, second entry would be 1/4, second third. So I can say this is the defining formula or the preceding formula. You can simplify it as, by the way, you can write it together as negative 1 divided by 2 to the power n. Is another way to write it. Simplified version. Okay, again, not that easy always, but let's see. We can generate more. So here's another example. Given the first, this is supposed to be a4. Given the first 4 term of this sequence, can you come up with the defining formula? What is the formula for an? As I said earlier, it is important to notice if you're dealing with alternating signs. So here plus minus plus minus. So I should have a negative 1 to some power n. But here's the issue. If I pick n to be simply 1, what do I get is I get negative 1 to the power 1, which is not correct. So the first entry would not be negative. So what I'm going to do is I'm going to add a 1 here. So now if I let n equal to 1, what happens is you get negative 1 to the power 2, which is positive 1. If I pick n equal to 2, then I will get negative 1 to the power 3, which would be negative. So now the signs match up. Negative, if I pick n to be 3, then I will get negative 1 to the power 4. This might be plus 1. And then you notice this is plus, this is minus, this is plus. So now the signs match up. So in the cases when you start with positive, then go negative, this is the coefficient, negative 1 to the power n plus 1. If you start from negative, you just pick negative 1 to the power n, because that matches the coefficient sign. Now, the denominator is quite easy. You can look at the denominator separately. What does this sequence represent? If you look at this sequence, 5, 25, 125, 625. Normally, you should break down the sequence if you can. What would be the formula for the sequence? It should be quite easy. It should be 5 to some power. If n is 1, then you get 5. If n is 2, you will get 25, and so on. So this is the denominator sequence. What about the numerator sequence? What you have is 3, 4, 5, 6, and so on. So this sequence could be represented by simply n plus 2. If you let n to be 1, then you have 3. If you let n to be 2, then you have 4, and so on. So it's one important thing is that here I start with n equals to 1. Here again I start with n equals to 1. You can start with n equals to 1. These all have to match so you can combine them together. You cannot start here with n equals to 3, down here with 2, and so on. So it's important that you pick this coefficient, the starting point to match. Then you can combine them together and say, okay, an is basically negative 1 to the power n plus 1 multiplied by the coefficient of the numerator is n plus 2, and the denominator was 5 to the power n. So this is the an, assuming n starts from 1. Okay, it's a good idea to always break down, if you're dealing with fraction, the numerator and denominator separately. Sometimes you can't do that. In this case, it's quite easy. By doing that, you can find out the formula. Okay, sometimes we deal with recurrence relations. What does it mean? That means the next sequence would be defined based on the previous entries. So if you have the first and second and third term of the sequence, you define the fourth term based on those terms, and so on. So the fifth term would be defined by the previous ones. A very important example is the Fibonacci sequence. The sequence depends on only two terms, the two previous terms. So if you're given f of 1 and f of 2, f is used for the Fibonacci. So here, if f of 1 is given 1, f of 2 is given 1, then the third entry, f of 3, is defined just by adding those two, f of 2 plus f of 1. The fourth entry is defined by adding the third and the second. And the fifth will be defined based on adding the fourth and the third terms of the sequence. And in general, you can create this structure and say f of n is defined by f of n minus 1 plus the entry before that, f of n minus 2. So here when you see the sequence recurrence relation, it means the nth term is defined by adding up the n minus 1 term plus the n minus 2 term. The sub-indices are just telling you which term are you adding. And the assumption here is n is 3, because we already have n equal to 1 and 2. You cannot replace the 1 and 2 in this equation, otherwise the sub-indices would be 0 and negative. So if you start with the third sequence, so here what you get is, if you replace n with 3, what you get is exactly this. F of 3 would be f of 3 minus 1, which is 2, plus f of 3 minus 2, which is 1. So these sequences, the sub-indices match up with this notation. This is for n equals to 3. For n equal to 4, we get this, n equal to 5, and so on. So what are the sequence terms here? F of 3 would be 2 plus 1, sorry, f of 2 plus f of 1, which is 1 plus 1, so it would be 2. What would be f of 4? f of 4 would be f of 3, which we already calculated, 2, plus f of 2, which is 1. So you get 3. F of 5 would be 3, plus the previous, so it would be sum of these two. It would be 3 plus 2, which is 5, and so on, if you continue. It would be quite easier if I write it this way. The first element is 1, first entry, the first term. Second term is given 1. Third term would be sum of these two, which is 2. Fourth term, sum of these two, 3. Fifth, sum of these two, which is 5. And the sixth entry would be sum of these two, 8, and so on. You can continue. 13, 21. If I give you this sequence originally, it's quite difficult to come up with this formula, the Fibonacci formula, without knowing that this is a recurrence relation, because there is no kind of structure to it unless you know that you're using this summation of the previous terms. So it's not always easy to come up with a formula, and the recurrence one is maybe the most difficult. Okay, what you notice here about this Fibonacci is, by the way, is that the terms are increasing. So if I let n get bigger and bigger, what you have is the corresponding terms are larger and larger. So you end up in thousands, millions, and so on. So what is this behavior of this sequence? Is basically the sequences keep increasing. As you increase n, as n is increasing, what happens is that the f of n will also increase. Okay, so what we can say is, now we can say, let's discuss the behavior of a sequence as you let n to be very large. And that's what we call it, the limit of n, an. So sequence an has a limit L, and we write the limit, the limit notation, limit an as n approaches to infinity equals to L, or sometimes they say as n is approaching to infinity, what is an doing? N is approaching L. If this limit exists, then it means the sequence is convergent to a number. If that limit doesn't exist, then the sequence is divergent. An example of a divergence is exactly this Fibonacci. If I increase the n, what happens? You will get, these numbers will continuously grow. So this would be 34 and so on. So as n is getting very large, what happens is the corresponding f of n would be increasing toward infinity. Therefore, it's not convergent. But there are examples where the limit is approaching to a certain value. Here are maybe a couple of two examples. Let's see if they're convergent or divergent, and then can we calculate the limit. So the convergent here, let's say an is given n divided by n plus 1. Let's find out a couple of terms of this sequence. So this is for an. What is an? An is, first term of the sequence would be 1/2. Second term would be 2/3. Third term would be 3/4, and 4/5, 5/6. So as n is increasing, if I pick n to be like 100, I'll get 100 divided by 101. If I pick n to be like 1,000,000, I'll get 1,000,000, 1, something, I'm missing a 0 probably. Divide by, 1,000,000 divided by 1,000,001. There you go, and so on. So now, our idea is, what happens if we let this n to be as large as possible? What happens to these numbers? Are they approaching a certain value? And I think you can use decimal value to estimate, but what you can see is here, maybe this is close to 0.99, something like that. This would be close to 0.9999 something in this form. And as you let n to be larger and larger, these values are getting closer and closer to value of 1. So I can say that the limit n divided by n plus 1 as n approaches to infinity is basically 1. We can say this by actually calculating the limit. If you remember, if you remember the infinity limits from Calc 1, you should say, okay, this is simply a limit the largest term divided by the numerator, the denominator as well divided by the largest term, 1 over n. Then you can simplify it, divide each one by n as n approaches to infinity. Numerator is 1, denominator would be 1 plus limit 1 over n as n approaches to 0, infinity would be 0, so you'll get simply 1. So this would be kind of how you show that the limit is approaching 1. So that means the sequence an approaches 1 as n approaches infinity. So this sequence is convergent to a certain value. That value is 1. And you can look at these numbers on a graph. How can you look at this? You cannot draw it continuously. What you can do is, okay, let's say this is n, this is an. Okay, if n is 1, what do we get is, we get n is 1, we get, say, 1 half. We have this point 1 and 1 half. If n is 2, what you have is 2/3, so 2/3 somewhere. Sorry, 2/3 is high. There you go. 2/3 somewhere. Let's say this is 1. 2/3 somewhere there. And if n is 3, you get 3/4. So these numbers, 4, 5, 6, are getting closer and closer to 1. As n is approaching to million, then these numbers are getting very close to 1. So what we expect is, as n is approaching infinity, an is simply approaching to 1. So this is a convergent sequence. On the other side, if you look at Bn, what do we have for Bn? Was n squared divided by n plus 1. N squared plus 1 divided by n plus 2. Sorry. So that's 1 divided by n squared, n plus 2. So now, if you calculate a couple of terms of this sequence, Bn, the first entry would be replacing 1, you'll get 2 over 4, 1 half. So if you replace n equal to 2, you'll get 5 over 5. If you replace n with 3, you get 10 divided by 6. Replace n with 4, 17 over 7, and so on. If you replace 100, you'll get 10,001 divided by 103, and so on. So what you can see is at the end, what happens is these fractions are keep getting larger and larger. The numerator is increasing very fast compared to the denominator. Right, so it started with 2/4, then 5 over 5, greater than 1, greater than 2. This is almost 2. This one is greater than 2. Then 10,001 divided by 103 is greater than 100. So on. So this n is quite increasing. As n is increasing, Bn is also increasing quite fast. So what happens is that this increasing part is approaching toward infinity. And we can calculate the limit to see if the limit exists. N squared plus 1 divided by n plus 3 as n approaches to infinity. You can say this is limit, exactly the same idea. N squared plus 1 divided by, you can divide by n squared if you want, the largest term, and divide by n squared plus 3 divided by n squared as n approaches to infinity. So what we have now is numerator simply becomes 1 plus 0 divided by 0 plus 0. This is an undefined value. That means if n is increasing, this is approaching infinity, positive infinity. That means by letting n increase, Bn is also increasing super fast toward infinity. So this is a divergent sequence. And so this one is a divergent. On the other side, for the an, we have a convergent sequence. Okay. There are certain theorems that you can use to kind of calculate these the convergent limits. One of them here is the fact that if you have an as 1 divided by r to the power n, so if n is positive, what you know is that 1 divided by r to the power n, again here let's assume r is a number greater than 1. Sorry, here I forgot. R is a positive number. If you have a positive number and you let this is, I don't think this is correct. I think this is supposed to be greater than 1 here. Sorry about that. Yeah, so if the denominator is greater than 1, then what you have is simply you'd have a convergent. So if you have 1 divided by 2 to the power n, that would be a convergent sequence. If r is less than 1, then this kind of is going to be a divergent. So if r is less than 1, then the limit would be divergent, because the denominator would be decreasing very fast, and then the fraction is increasing towards infinity. Okay, so this is one of the uh, main uh, main theorems that we will use later on for comparison. But at the moment, let's just say that if we're dealing with a fraction, if the numerator is, if you're dealing with something like an, some number r to the power n, if this number is less than 1, then this sequence is convergent. It is convergent if it's less than 1 r. That means that if you look at the fraction of it, r must be greater than 1, because 1 divided by r would be the reciprocal. And if this r is greater than 1, then you would have a divergent sequence. Okay. And if it was the other way around, I think that's what I wanted to show at the beginning, not this. I wanted to write the other way, n to the power r, maybe. In that case, if the denominator has a positive exponent, if r is positive, then we have a convergent sequence because the denominator is increasing. And if r is less than 0, then you can flip the fraction and make it n to the power positive exponent. Then in that case, you would have a increasing sequence toward infinity, which is a divergent case. You don't need to memorize this. This would become natural after a while. So you're just looking at the limit. Here's another one. It's a combination. If you have two sequences, A and B, and these sequences are convergent, then the combination of these two you can calculate the limit. So if you're looking at the limit of some of these two, you can calculate the limit of each one separately and add them up. If you're looking at the difference of these two sequences and looking at the limit of that, then you can calculate the limit of each term separately, each sequence separately, and subtract it. If you multiply a constant to one of the sequences, then the limit would be just keep that constant and multiply by the limit of the sequence. If you're dealing with a constant sequence, so if your sequence is constant, the limit is the same as that constant. This is a simple example would be if you're looking at this sequence 1, 1, 1. What happens at the infinity? You still expect 1 at the end. So this is a constant sequence. The limit doesn't really depend on anything. If you're looking at the product of the two sequences, an and bn, assuming that an and bn again have limits separately, then you can calculate each limit separately and multiply those. If you're looking at the division, here's the important part. For the division, the denominator cannot be 0, otherwise this is an undefined value. So if the denominator is not 0, you can calculate each one separately in divide. If the denominator is 0 and the numerator is 0, then in that case we can use the Hopital rule that we learned in Calc 1 to calculate the limit. And if you're dealing with an to some power, you can calculate the limit of an without the power, then evaluate the power at the end. These are very basic limits that we learned for functions as well. The same idea holds for the sequences. And the squeeze theorem, you can use it for the sequences as well. If you have a sequence Bn, which is between the two sequences An and Cn, for very large n's, this means for a very large n, then if at some point this is a true statement, that's what it means. This is for n greater than n naught. This means that at some point, if the sequences are bounded between these two, if Bn is bounded between these two, and you know the limit of the out ones, you know the limit of An and Cn limit, and they both turn out to be the same thing, then that kind of tells you that Bn must be between the same number. That means Bn must be exactly the same limit. This is called the squeeze theorem. You've seen it for a function, the same idea. Again, you can extend it to sequences. This is the limit Cn and A, and these are the upper and lower limits. Okay, finally, if you take a limit of a sequence with absolute value, and that limit is 0, that tells you that the limit without absolute value still would be 0. So that absolute value doesn't affect the limit if it's simply 0. If it's a positive number or then you can't say anything about the A. So here, make sure that if you're looking at something like -1, 1, -1, 1, if you're looking at this sequence, we call this an, then limit absolute value of an as n approaches to infinity would be simply 1, because whatever you put in as in the limit, you'll get 1 as the result. But you can't say anything about the limit an as n approaches to infinity. This one, we don't know. Does not exist, I should say. Because you don't know if the answer is 1 or -1. Because they alternate. So it is important that you use this theorem only if the result is 0. Okay. Here, let's do a couple of examples. I wrote 5 different sequences and ask you to find the limits. You should always pause this, try it yourself before I calculate the limits. So let's calculate, start with an. Limit, this is an. Limit 2n plus 1 divided by 3n minus 2 as n approaches to infinity. If you remember, if you replace n with infinity, you get infinity over infinity, right? This is kind of what we learned if we're dealing with functions. You can always use the Hopital rule. You can assume that you have infinity over infinity, use the Hopital rule. Simply what you get is limit 2n plus 1, the limit of that would be, derivative would be 2, derivative of the denominator would be 3, as n approaches to infinity. And that is 2 steps. Okay, you assume n is continuous in this case. You can replace this variable x if you want. You can keep it as n. The same structure. So this is a fast way to calculate the limit. But the only thing you need to make sure is, do you have infinity over infinity? Is it indeterminate form or not? How about if we're looking at the limit of Bn? Limit n divided by square root of 3n plus 2. There's a way to bring the n inside the square root. I can show you that, or you can use the Hopital rule. Try to use Hopital rule yourself. You should be able to get the same result because you would have infinity over infinity. But what I'm going to do is I'm going to divide both numerator and denominator by n. Just to show you what happens is, if I divide this by n and divide the denominator by n, what we get is 3n plus 2 divided by n. Okay, instead of n, I can write square root of n squared. That's the same as n, right? So I can combine the two square roots and put the n squared inside. So what I'm going to do is I'm going to divide by n squared inside. Because the square root of n squared is exactly the same as n. So I divide the numerator and denominator by the same time. Limit, what would be the numerator? 1. And the denominator here would be square root of 3 over n plus 2 over n squared as n approaches to infinity. By the way, last example I forgot to mention, here we're dealing with a convergent sequence since an is bounded approaching to the limit of that existence, 2/3. So how about this one? Now as n approaches to infinity, what you have is 1 divided by square root of 0 plus 0. Limit 3 over n would be 0, limit 2 over n squared would be 0. So this is infinity. Sorry about that. That tells us that the limit didn't exist and we have a divergent sequence. Divergent. Okay, let's try Cn. Again, you should be able to use Hopital rule here as well. But I wanted to show you can use this same structure that we did earlier on. Calculate the limit even if in whole square root it still holds. But here is the issue, you cannot always do that. So we kind of have to be able to go back to the Hopital rule and use that. So in this case, if you replace n, you'd have infinity over infinity. Ln and approaches to infinity is infinity. So there is no choice except taking the Hopital rule. Apply the Hopital rule. So here, if I apply the Hopital rule, derivative of the numerator 1 over n, derivative of the denominator is simply 1, then approaches to infinity. And this is limit 1 over n as n approaches to infinity. That is 0. So what can it tell us? It can tell us that we have a convergent sequence. And the limit of that sequence would be simply 1. Okay, sequence number Cn and Dn. Sequence limit -1 divided by n. -1 to the nth power as n approaches to infinity. Okay, you can replace n with infinity, but what I'm going to do is I'm going to use the theorem that we learned. Let's look at the absolute value of -1 to the power n divided by n. What happens if I look at the absolute value? If you're dealing with the negative with the alternating form, it is always better to deal with the absolute value. So what does this absolute value do is take care of the negative sign. Negative with absolute value of negative would always be positive, so you'd have simply limit 1 over n. And as n approaches to infinity, this is simply 0. So now by the theorem we have here, if the absolute value has limit 0, then the limit of the sequence itself would be 0. So I can say this limit is also 0. So I have a convergent sequence. Okay, this was dn. How about en? En is cosine n divided by n. So let's try that. En is cosine n, sorry, I forgot the limit cosine n divided by n as n approaches to infinity. Here is one issue. If you replace infinity, what do you have for cosine infinity? You have no clue what is cosine infinity. It could be 0, 1, -1, root 2 over 2, whatever that is. So this is not a good choice to calculate this limit. What we can do is, we can use that squeeze theorem that we had. What do we know about cosine? Cosine n. Cosine is always bounded between -1 and 1. So if I have cosine n, it should be bounded between -1 and 1. And then if I divide by n, what I have is -1 divided by n is cosine n between divided by n is between -1 over n and positive 1 over n. So now let's calculate the limit of the outside. So I'm calculating the limit of the outside sequences, these two sequences, 1 over n and negative 1 over n, to see what happens to these two limits. What is the limit of negative 1 over n? As n approaches to infinity, this would be negative 1 divided by infinity, simply 0. Limit 1 over n, exactly the same thing. So what does it tell me? It tells me that these two are approaching 0, as n is approaching infinity. The sequences are approaching 0. So by the squeeze theorem, this has no choice but to approach 0. So I can say the limit of cosine n divided by n is simply 0. And this is a convergent sequence. Okay, so try to do a couple examples yourself and sequences limits. I'm gonna stop at this point, and then we will continue next time or talking more about the sequences, increasing and decreasing sequence, but I don't want it to be super long, this section, so I'm gonna stop at this point.